Good afternoon, good evening. So today I will talk about multi-labeled trees and bipartitions. Yeah. Multi-labeled tree. So I think I will start with defining what a multi-labeled tree is. So, yes. So this is a phylogenetic tree. So a tree with a root, a unique path from the root to each of the leaves. And the leaves, they represent species, they represent organisms, they are all distinct. So they can be numbered. You have here leaves from 1 to 5, which gives a leaf set, X, 1, 2, 3, 4, 5. And for multi-labeled tree, the leaf set is allowed to be a multiset. So you are allowed to have multiple copies of each leaf, which from a theoretical point of view make a lot of things more difficult. But before going to the theory, before going to the mathematics of these structures, I wanted first to show you a few examples of where the MUL-trees arise in the literature, in phylogenetic studies. So I will today highlight 3 examples, namely polyploid studies, biogeography studies, and phylogenetic networks here. And there are other examples, of course. So polyploidy first. So a polyploid organism is an organism that has more than one copy of its genome. This can arise via genome duplication, via hybridization. And distinct copies of a given genome, they may have a different evolutionary history. So for example, this is an example from a paper studying some species of plants, where you can see the species SA, SS, SI, and SU. They don't have the same number of copies of their genome. So the tree itself represents the history of the genome, and they are labeled with the species they belong to, which means that, for example, the species SS, which has 3 copies of its genome, it appears twice in the 3 times, sorry, in the leaf set of the tree. Species SI appears twice. So this is a tree that has been reconstructed from some phylogenetic technique from these genomes, and this is a multi-labeled tree. The other example, and an example I like, is biogeography. So biogeography, I like this definition I found in a paper. It's the study of the geographic distribution of organisms. It seeks to understand ecological processes like climatic stability, effects of area, that influence the distribution of living organisms over a short period of time, and to uncover events occurring in the distant past, which has resulted in the geographic distribution observed today. So what does it mean? The people who studied biogeography, and in particular, the people who wrote this nice definition, they start with a phylogenetic tree of some set of species, and they look at the geographical distribution of these species. So for example, you have a map cut in distinct regions, and you identify the region in which each species lives. And now in your phylogenetic tree, you can replace the label of your species with the code of the of the region it belongs to. And this, the author of that paper I mentioned, they call this an area cladogram, which is, in the sense of my definition before, a multi-labeled tree. Just to be precise, the previous example, the polyploid one, it was a real example. This one is a toy example, so no correspondence in reality. I made up the map. So that's for biogeography. The third use of MUL-tree I wanted to mention is the link of MUL-trees with phylogenetic networks. So, and more precisely, the MUL-trees, they are an alternative way of representing phylogenetic networks. So look at this network, for example. You can basically record all the paths from the root to a leaf by disentangling all hybrid vertices. So basically, each hybrid vertex, you separate the incoming arcs, and you duplicate everything that lies below the hybrid. So for example, you take apart the hybrid over leaf 2, it gives you this. Take apart the hybrid over leaf 3, and you take apart the hybrid over the subtree 2, 3. And this gives you a multi-labeled tree. And the good thing is you can do it backwards. So by just identifying isomorphic subtrees, you can reconstruct the phylogenetic network. So it's important to note that you don't always get the network you started from, but that's not my topic for today. So if you want to know more about this, you can have a look at one of these two papers. So now that I've given a bit of context, I will go into the underlying structure of multi-labeled tree. So I will look at the unrooted version. We forget about the root, we forget about the direction. And a nice property of trees as graphs is that when you remove an edge, any edge, you get exactly two connected components. And that leads to bipartitions of the leaf set. So if you remove an edge, you get a bipartition in terms of the leaf set of one of the components versus the leaf set of the other component. And that bipartition, it's called a split. So if you do it for all edges, you get what is known as the split system induced by the tree. To keep this simple, I will ignore the so-called trivial splits that are splits obtained by removing edges adjacent to leaves. So they should be considered, but their role is not that important, and that will allow me to show you examples with split system of manageable size. Otherwise, things will get messy. So split systems induced by phylogenetic trees. So phylogenetic as opposed to multi-labeled trees, they are well known since 1970. And the split system of trees, they have been characterized in terms of what is called compatibility, where we say that two splits A, B, and CD of a set X are compatible if one of the shown inclusion holds. So basically one set of the split number 1 belongs to one set of split number 2, or the other way around. Not belongs, but is included in. And the theorem that dates from 1971 is there exists, if you have a split system, there exists a phylogenetic tree T such that your split system is precisely the split system of the tree, if and only if any two splits of your split system are compatible. So it's a result due to Uneman 50 years ago. So that's for phylogenetic trees. That's for leaf sets, not multisets. Because, as I said in the introduction, when you look at multisets, things become very complicated. So first observation, this nice theorem does not hold in the multiset case. So you have that these three splits, they are pairwise compatible, but it can be easily checked that no tree displays all these splits at the same time. So first observation, the theorem on compatibility doesn't hold. And bad news, it has been shown in 2008 that a split system, if you have a split system on a multiset X, it is NP hard to decide whether there is a MUL-tree displaying that split system. So a MUL-tree representing all these splits. But we can still do things. So to look into what goes wrong for the multiset case, we looked into the properties, the key properties that are used in the proof for the compatibility results for sets, for phylogenetic trees. And there are two key properties that are trivial when you are looking at sets, namely that if you have two compatible splits, then you can only have one of the, at most one of the four intersections I mentioned before can hold. You cannot have more than one of these inclusions. And second one is even more trivial. If you have three sets, A, B, C, A is in B and B is in C, then the union is in C. It makes sense because we are talking about set unions. So if an element is both in A and B, then it's not counted twice. But of course, multi-set unions, they don't work that way. If you have an element in A and an element and the same element in B, then that element will appear twice in the union. So first observation, none of these two key properties hold when we look at multisets. So we need to find some situation in which we can get some equivalence to these two properties. So the first thing we looked at, because we are looking at inclusions, set inclusions. So we introduced a graph from a split system that is called the split-containment graph. So how does this work? Basically, you take all your splits in your split system. So here in my example, there are three splits. And each of on the vertices of your graph, they are all the sets induced by the splits. So each split induces two sets. So you have 2 times number of vertices in your containment graph is 2 times number of splits. And then you add a directed arc from one set to another if the first set is contained in the second one. So for example, this is the graph. So you can see that AB is contained in BC, BC contained in ABC, and so on. We don't care about vertical edges. We are not interested in the property that one set of a split is contained in the second one. We really want to pairwise compare the splits. So that's why you don't see vertical arrows. Also, there is inclusion in all three cases, actually, of the top set into the bottom one. And the interesting thing is, so this is a representation of the split system I mentioned before. This is not. So yeah, this is a representation. And this representation, this MUL-tree displaying my set of split, it is closely related to a specific subgraph of my containment graph. So again, I will start with all sets induced by the split as a vertex set. And now we add an arrow from set A to set B. If the part A of the first split is contained is part B of the second split. So what does it mean? So the example, if you consider the split AB, so the part AB, I don't know, do you see the mouse if I move it or not? Yeah. So this is the part AB of the split AB versus AABB CCC. And this is the part AABBCC of the split ABC. So also AB is contained in both ABC and AABBCC. Don't want to click. The AB part of the split AB versus the rest is the AABBCC part of the second split. So we do this for all sets. So it's also AB is also contained in the AABBCC part of the BC versus the rest split, which corresponds to that edge. So if you have one arc, you have quite naturally the anti-parallel arc as well. So if AB is contained is AABBCC, then ABC is contained is AABBCCC. And finally, we need to compare these to the split 2 and split 3. And you have the BC part, which is contained in the ABC part of the split number 2. And so the anti-parallel arc. And this, because each arc has its tail contained in its head, this is a subgraph of the split containment graph I mentioned before. If I now look at a different representation of the same split system, we obtain a different subgraph of the split containment graph. So the question is, what are the interesting properties of these subgraphs that are linked to three representations? And these graphs, they satisfy two properties. So the first one I mentioned before, for all pair of split ABCD, if you have an arc in one direction from a set of split 1 to another set to a set of split 2, then you have the complements of these two sets. They are linked with an arrow of opposite direction. So basically, it means that in the subgraph, the restriction of G of the subgraph to the vertex set ABCD has this is isomorphic to this graph. And the other thing that is not obvious at first, but that is very, very useful, is for all vertex P. If you take the union of all sets, the multisets union of all sets A, such that AB is an edge of your subgraph, then this multisets union is contained is B. So these two properties, they are quite similar in essence to the properties I mentioned about compatibility in the set case. And these properties, they are enough to guarantee that you can find yourself a tree representing your split system. So that's actually a characterization. If there exists a subgraph of your containment graph satisfying one and two, then there exists a MUL-tree representing your split system, and the other way around. So this is the characterization. This is a characterization of split systems induced by MUL-trees. So one direction we discussed already. So now the interesting question becomes, okay, so if I have a subgraph satisfying one and two, how do I find myself a tree from this subgraph? How do I build a tree representing my split system? So this is the algorithm part of my talk for this algorithm and complexity seminar. So I wanted to have an algorithm part. Yeah, before that, I forgot the number of non-isomorphic MUL-trees representing my split system is in one-to-one correspondence with the number of non-isomorphic subgraphs of my containment graph satisfying 1 and 2. So that's interesting because that tells you how many distinct representations you can find. That gives you a characterization of split systems for which there is a unique tree representing the split system. And yeah, as you have seen before, we started with, I showed you example on 2 trees, and each of these trees, they induced distinct subgraphs of the containment graph. So now, as promised, the reverse operation. So here is a subgraph of my containment graph satisfying property 1 and 2. So the first thing we do is to get rid of the non-useful edges. So an edge is considered useless if you can get from one of its extremities to the other via a different path. For example, to go from AB to AAABBCC, you can go directly, or you can go there down and right. So the arc AB to AABBCC, it's not useful. And the same holds for the arc from BC to AABBCCC. We don't need them. We only, to build the tree, we only need these 4 arcs. And now we look at each set. So we look at AB first, and we will make some collections of sets. So we will define some sets of sets. Yeah. So sort of an equivalence relation on this set of sets. So we associate 2 sets if I will say it differently. So the edges associated to AB are the edges, the sets associated to AB are the sets you can reach in the graph from the complement of AB. So here you see that AB, you take its complement, and this is this has out degree 0, so you cannot get anywhere from AABBCCC. So AB is alone in its equivalence class. If you look at AABBCC, you take the complement AB, and AB goes into AABBCC. So these two sets are put together. It's symmetric because of property 1. If there is an edge arc from AB to AABBCC, there is an arc from the complement of AABBCC to the complement of AB. So it doesn't matter in which order you look at your sets. It's a symmetric relation. So AABBCCC is associated to AABBCC. ABC, take the complement, it goes into AABBCCC. So these two sets are together. And finally, BC, take the complement, there is no arc going from there. So you have BC alone in its class. So next step, now that you have all these classes, you join two classes by an arc if they contain two complement sets. So for example, this one contains AB and AABBCCC, so it's associated to this split. So you put an arc in between these two. Between these two, you have the two sets of the second split, ABC, AABBCC. And here you have BC here and its complement here. So you get three edges for three splits, which makes sense so far. Now we have to find the labels of all these vertices here. So we have 4 vertices to label. And what we do is, for each equivalent class, you take one element of the class, you consider the set minus the union of the sets associated to incoming arcs. So for AB, you have no incoming arc. So this, okay, put it all together. So for AB, you have no incoming arc. So this vertex at the top here, it will be labeled AB. This one, if you look at AABBCC, you have one incoming arc. So if you take AABBCC minus AB, you get ABCC. Interestingly, you get the same thing if you look at the other set in that equivalence class. If you take AABBCCC and you remove from there ABC, you also get ABCC. And that's a nice property of this this subgraph of the containment graph. So that's a consequence, a non-trivial consequence of the properties 1 and 2 I mentioned before. It's that regardless of the set you consider in the equivalent class, and you remove all sets from incoming arcs, you always get the same set. So we can label the corresponding vertex of the tree with that set. So again, AB here. Here we would have ABCC. Here we would have A. And here, because there is nothing into BC, we get BC. So this gives you vertex labels. So we don't care about the classes anymore. And yeah, now we have a tree. It's not exactly a MUL-tree in the sense that we don't have leaves, but I just said I would ignore trivial splits for the demonstration, but we could have included them in the algorithm or add them at the end like I will do now. It's the same thing. You get in the end a MUL-tree displaying the split system, which is exactly the MUL-tree corresponding to the subgraph we started from, which I didn't remind you of, which I didn't have, so which was, well, doesn't matter. Okay, so to summarize, we have a graph, which is the split containment graph. It is NP hard to find to decide whether there is a subgraph satisfying property 1 and 2, and if there is one to find it. But if you have it, there is a fast algorithm polynomial time algorithm to find a tree representing your split system. So just check the time. Yeah, so I wanted to conclude by mentioning a conjecture, which comes from the paper from 2008 I mentioned before. So if you have a multiset M, you can record the deviation of that multiset via a parameter delta, which is basically for each x in the underlying sets, you consider the multiplicity of x in M. Take this multiplicity by -1, you sum that over all x, and that gives you the quantity delta of M. So why is this quantity important? So there is a theorem still from the same paper. If you have a split system on a multiset, there exists a tree representing your split system if and only if every some multiset of your split system of size at most max 2 delta or delta M delta plus 2 is representable. So this theorem, because of the quantity, it's helpful. It allows to break down the problem into smaller problems, but the quantity max 2 delta plus 2 is not very nice to work with. So the authors realized that also they have max 2 delta plus 2. They couldn't find any contradiction. They couldn't find any compatible set, any incompatible set such that subsets of size delta plus 3 or more are representable. So that led them to devise a conjecture, which is the following one. Basically the same theorem, except you replace max 2 delta plus 2 with delta plus 2. So the conjecture was put in 2008, and that was actually the starting point of our work on that question, even before the characterization, the graph, and the algorithm I presented to you. And bad news, we didn't manage to prove or disprove the conjecture. So we only have so far partial results. We have one which implies to look at some annoying property enjoyed by subsets of your split system sigma of size delta plus 3. So if all subset of size delta plus 3 satisfy this annoying property, namely that in the split containment graph, you have a vertex that has in degree 0 and out degree delta prime -1, which means that your set A doesn't contain any set from your split system. And for each other split, it's contained in exactly one of the sets of the other split. So it's a painful requirement, but if it's satisfied, then the result with the delta plus 2 holds. Another much easier, but probably not too helpful in real life result is if all the splits have the same size. So the size of the split being defined as the size of the smaller set that composed the split. If they all have the same size, then the result holds. The delta plus 2 conjecture holds. And finally, if all your splits have size 3 or less, so if you only consider a small split, then we don't have the delta plus 2 boundary, but we have delta plus 3, which is for large multisets M already much better than 2 times delta. So the conjecture is still open. We don't really know what to do next, what the next step towards this conjecture solving would be. So any idea are welcome, really. So if you are interested in working on that, if you are interested in seeing in details all the proofs of what we have done, please let me know. The proofs themselves, the results, they can be already seen in a paper that we submitted 2 months ago, which is already on archive since yesterday. So you can go and have a look. Yeah, and I would like to thank Vincent Moulton. So I didn't say it at the beginning, but every time I say we did that, we studied that, I meant Vincent and myself. So we worked on that together. Of course, I don't forget Cassie. She was not Katharina Huber. She was not directly involved, but she still helped us. I would like to thank the cities of Norwich and Sheringham because some ideas for some of the proof arose when I was working there. So always nice to get some fresh air to change your environment to get new ideas. And yeah, to conclude, I just would like to dedicate this talk to my colleague and dear friend, Yulia. So Yulia is a Russian with part of her family in Ukraine. So she's having a difficult time at the moment. So I just wanted to send some love to her and to everyone suffering from this nonsense. Thank you.